Microscopic origin and universality classes of the FEM of ThreeBody Parameter. And what I'm going to consider is this system. So just three identical bosons with short-range resonant two-body interactions. And I will make the following assumptions: that these two-body interactions are described by just a single scattering channel, and that there are no three-body interactions. Okay, so first of all, I would like to give a summary of the results I'm going to present, just to convey the main message. And the main message is that so our results seem to show that the three-body parameter is essentially determined by two-body physics, and in particular what I call this two-body correlation, and I will explain what it means. And the reason for this is that two-body correlation imposes a deformation of the three-body system. And the consequences of that is that the three-body parameter is typically, in general, on the order of the two-body effective range, determined by this length scale. And it admits different universal values for distinct classes of interactions. Yes? Not necessarily, because the two-body interaction can have several length scale.
Not all of it. I mean, like the first statement, right? So you said the three-body parameter is determined by two-body physics. Well,
yes,
if there's no three-body.
That's right. That's right. That's right. But more precisely, it's determined by what I call this two-body correlation that I will show in
So this is off-shell properties of the two-body T matrix.
Absolutely.
Right? So then that's all there is. Once you know the half off-shell two-body
Okay.
T matrix, that's everything.
Okay. So what I call this two-body correlation actually corresponds to the zero energy two-body wave function. So that's more specific.
So that's
the on-shell. It sounds like you're talking about the on-shell.
I don't think it's just on-shell.
No.
The scattering.
No, but I'm going to talk about off-shell, so I will show.
It's the shape of the two-body wave function at zero energy.
Absolutely.
You would say if I know the two-body T matrix at zero energy, then I know everything.
Of course, yes.
Okay.
Okay.
Too much coffee.
Any questions? Okay, so let me remind very briefly. Probably everyone here knows what the three-body parameter is.
Can you speak up a little bit?
Oh, sorry.
Thank you.
So, so anyway, let me just very briefly remind you what it's all about. So, if we consider particles at low energy, so the two-body interactions can be described by a single two-body parameter, which is the scattering length, and that describes nicely the scattering properties at low energy and the low energy bound state. And that's the typical length scale. But Vitaly Efimov found in the 1970s that if you have three particles, there appears an effective three-body attraction between the three particles, which scales like 1 over r squared, where r is this hyperradius defined this way. So that's the kind of global size of the three-particle system. And as a consequence, this attraction tends to make the system collapse. And one has to introduce a three-body boundary condition here in order to regularize the problem. And this introduces a new length scale in the problem, and that is referred to as the three-body parameter.
It doesn't have to be a length scale. You're just fixing the phases of those waves in the deep potential.
Yes, that's right. That's right. But in practice, you have to introduce a length scale, because
well, the mathematicians could do this by introducing self-adjoint extensions of the Hamiltonian, but I know more physically it's a radial cutoff.
Okay, I mean, yes.
You could also view it as a quantum defect parameter of a certain kind.
Yes, I will show this.
It's another language for the same thing.
Yes, actually, I will show a picture simultaneously.
There is the lowest energy, and you can convert that to a length.
That's right. That's right. Yes. So, so then you get these bound states, three-body bound states, and here this is what they look like as a function of 1 over the scattering length. And so, yes, for example, here at unitarity, when the scattering is infinite, you have no more length scale from this parameter, and then you need a new length scale or energy scale to determine the energy of this three-body bound state. And right, and that determines the length scale, and it can be measured by these quantities. So this is kappa. This is the binding wave number of this three-body bound state at unitarity, or this quantity A minus, which is the scattering length at which this three-body bound state dissociates into a three-body continuum. And yeah, so these quantities are correlated to this boundary condition that you impose. If you change the boundary condition like this, then you move the spectrum like this. Well, strictly speaking, the three-body parameter would be correspond to these quantities for highly excited states, close to this kind of accumulation point. But for this talk, I'm going to what I'm going to call the three-body parameter will be, in fact, these quantities which are associated to the ground state.
Show that animation again. I wasn't watching carefully when you did the animation. Can I just repeat
the animation? Can I go? Yes.
Wow.
Like this?
Do you want one now? Do you want one for your talks?
All right. So then, yes. So now the question is, so what determines these low energy parameters? So, for example, if we look more specifically at atoms, we know that their microscopic interaction, the two-body potential is something like this. There's for neutral atoms, there's van der Waals tail at large distance, and then there's some more complicated short-range details. And very naively might think that, okay, maybe the length scale, the van der Waals length scale associated to this determines mostly the two-body parameter, the scattering length, but actually it's not true. We know that it depends sensitively on the short-range details. And just to exemplify this, I just plotted the triplet scattering lengths of various atoms as a function of their van der Waals length. And you see that there's no particular correlation. It's all over the place. So in that sense, there's no universality of the scattering length. But if now we consider the three-body parameter, we can have a kind of similar picture where we have this attraction at large distance, and then there's some short-range details. And then by analogy, we might conclude that in the same way, so as Paul said, we can view it as some kind of quantum defect theory, and we need to know some quantum defect here to determine this the three-body parameter, and it's not going to be easy to predict. But over the last few years, there's been experiments where they could actually measure this corresponding quantity A minus, and it was shown to correlate very well with the van der Waals lengths of these various atoms. So more specifically, A minus is roughly equal to -10 times the van der Waals length. And this has been referred to as the universality of the three-body parameter. Is that all right? Yes. Okay, so and then there was three-body calculations by Jia Wang, Jose Dincao, Brett Esri, and Chris Green, who is here in the audience. And they did a calculation, three-body calculation with van der Waals interactions to interpret these experimental results. And what they found is that if we look at the hyperradial potential, so again, at large distance, there's this effect of attraction, and then at short distance, there appears a repulsive barrier at a hyperradius around twice the van der Waals length. And the consequence of that is that the three-body parameter is set to this as a function of the van der Waals length, and it turns out to be for many potentials around -11 times the van der Waals length, which is consistent with the observations. And in this work, they stated that the origin of this three-body repulsion is suppression of probability in the two-body sector. And this is something we wanted to understand a bit better, and we looked in more detail. So,
what is panel C over there? The last
sorry?
panel on the far right? What is that?
Oh, sorry, these are experimental data. Yes. Yes, that's right. So let's look at first at two-body physics. So here I represent the scattering wave function at finite energy between two atoms. So this is, or two particles. This is their scattering potential. So at large distance we have this free wave. Which is just like a sine wave with some phase shift, and this phase shift corresponds to, at low energy, to the scattering length, and is caused by this potential. But at short distance, of course, it deviates from this free wave, and we have what I would call this TwoBody correlation. And so one may define it as, for example, the ratio between this full exact wave function and this free wave function. And here it doesn't make much difference, but if we look at scattering near unitarity, so near unitarity means that this phase is close to pi, which means that the free wave here is rather flat, close to the origin, which means that the correlation is more pronounced, and we have a strong depletion of probability here. And the typical radius for this depletion region, which I call R0. So for van der Waals interaction, it's very closely equal to the van der Waals length. By the way, in this talk, I will define the van der Waals length as 1/2 the mass, the C6 coefficient over h bar squared to the power 1/4. And more generally, the size of this correlation part is given by the half of the effective range, which is defined as the integral over the difference of probabilities between the correlated and uncorrelated wave functions. Right. So what is the effect of this correlation? So first, let's look at for three-body system in the context of zero-range theory, and here we plot. So we fix two particles at these positions and look at the probability of finding a third particle, and this is done using the hyperangular wave function coming from zero-range calculation.
Sorry, what are the axes on this graph?
So this is just space. So you have two particles. You have one particle here, one particle. So okay, let me show you. Yes, you have one particle here, one particle here. You just fix these two particles, and then for this fixed position, you calculate the probability in space of finding the third particle. And it turns out, as you can see, that the most probable configuration is when the third particle is close to one of the two particles. That's what you get from the von Efimov state. And this, at unitarity, this hyperangular wave function does not depend on hyperradius. So if you make these two particles closer, like this, it doesn't change the shape of this function. So you still find the same configurations. Okay. However, if now we do the same calculation with finite range interaction, here we use the Lennard-Jones potential, and solve the Faddeev equations to obtain this kind of plot. Now you see it's similar, but you notice the difference is that around each particle there's an exclusion region where the third particle cannot be. And of course it has this exclusion radius R0. And now if we make the two particles closer and closer, so yes, but still for this separation, the typical configuration still resembles the typical distribution of configurations for an Efimov state. Now if we make oops, sorry, I went too fast. If we make the two particles closer and closer, you see that because of this exclusion region, the distribution deforms, and eventually the third particle tends to sit between the two particles in a kind of equilateral configuration. So to understand this, we can plot all the possible configurations of...
Does it depend on the presence of repulsive core, or it will be no core, but just a deep attraction.
That's right. It doesn't depend on the presence of core. The only thing that matters is that there is a suppression of probability. And this can be due to either to a core or to some very deep potential, as I will show later. So here I don't make any assumption about the cause of this suppression of probability. We just have a suppression of probability, and that's it. Okay, so here are all the possible configurations of this three-particle system as a function of the hyperradius, so that's the size of the system, and this hyperangle alpha, which characterizes the geometric configuration from squeezed to equilateral to elongated. And as I mentioned before, for an Efimov state, the typical configuration is this elongated configuration. And you can calculate that for example, the average hyperangle is very close to pi over 6. Now, so as I said, there's an exclusion between the two-body exclusion between these particles. So here the radius of these balls here is R0, the exclusion radius. And now it's a simple exercise to find the configurations which are excluded because two of the particles are within that radius. And it turns out to be like this. As you can see, all these configurations are excluded. And then we can understand that if we have this kind of Efimov state coming from large hyperradius, when we reach this region, eventually, because this region is forbidden, the system has to deform to a more equilateral configuration. But this deformation has a cost. It costs some kinetic energy, and as a result, this configuration is also forbidden because it's too expensive to go to this region. And you see that essentially this phenomenon occurs roughly when the hyperradius is about twice the exclusion radius. So it's just a kind of explanation by hand of this repulsive barrier. So of course this is just a qualitative understanding, and then we want to confirm this interpretation. So the first thing we came up with is the simple idea. So clearly what's missing in the zero-range theory is this exclusion by two-body correlation. So let's consider a simple model, which is we just construct a hyperangular wave function, which is the hyperangular wave function in the zero-range theory, multiplied by a product of pair correlations, which creates some exclusion between particles. Oops, sorry, there's a... So, and then from that we can calculate an effective three-body potential, a hyperradial potential, in this way. And so at large distance, this is just one, so we just have the zero-range wave function, and we retrieve this Efimov attraction. But at short distance, what happens is that indeed it creates a repulsion, and that's indeed close to this hyperradius of about twice the exclusion radius. And it compares reasonably well with an exact calculation with Faddeev equations. However, I should say that this is obtained just from the so-called low-energy Faddeev equations, which is an approximation which neglects coupling to higher partial waves. And also, this is just for a single hyperangular channel. And if I were to take this potential to calculate, say, the three-body parameter, it would not be quantitative enough. It would be off by maybe a factor of 2 or more. So it's a good model to explain the origin of this three-body repulsion, but it's not quantitative enough.
A similar question.
Yes?
Suppose you just remove repulsive core.
Yes?
But with this deep attraction,
Yes.
will you get a similar curve?
Yes, exactly. Yeah, exactly the same.
In our paper, we did a soft wall van der Waals potential.
Yes.
And it has the same.
Yes. So then we scratch our heads, and as I was telling Daughter the other day, we tried to find many possible approximations, and eventually the one which seems to work better is this idea of using a separable potential. So replace the two-body interaction by a separable interaction. So separable interaction is it's a non-local interaction of this form. So it's essentially a projector. We project onto this kind of state chi and multiply by this constant xi. So it may look a bit artificial, but it's very convenient for calculations. It's very easy to solve the two-body and three-body problem with this kind of interaction. It almost behaves like a contact interaction. But it's richer than contact interaction. And in fact, it's possible to parameterize. So we have these two parameters, xi and chi. It's possible to parameterize this interaction in order to reproduce exactly the two-body zero-energy wave function of any potential. And it's given by this formula. So in momentum space, chi is equal to this expression, where here we have the zero-energy two-body wave function. That's the full wave function, and that's the uncorrelated, the free wave part. And xi is given by this expression. So you can show this. And then we have a model which, by construction, reproduces the scattering length exactly, the effective range exactly, and more generally, the low energy physics. So let me show you an example.
Just to clarify,
yes.
What you're calling the two-body correlation, is that the zero energy
That's
wave
the zero
function
energy,
as a
yes.
function of
Yes,
R?
the zero energy wave function. Yes, that's right.
So several nodes. So you reproduce all the nodes.
Yes, you can reproduce all the
All
nodes.
the van der Waals potential.
That's right.
And size 0 bar there is for infinite scattering length? Or what is size 0
Oh,
bar?
you can take any, actually here I have finite scattering lengths in this expression, but you can take any value of the
What
scattering.
is size 0 bar?
The difference between the interacting.
That's sine kr.
Yes, that's the zero. So, oh, this one?
Yes, what is
Yes.
that one?
Yes, for zero energy, it's just it's essentially R minus A, essentially.
Oh, it's a zero energy.
Zero energy asymptotic wave function. So it's very, very simple.
R minus A.
Yeah, I just wrote this for concision, but yeah, it's just.
But that would just be R, not R minus A, if it's non-interacting.
It's non-interacting, except at the
No,
origin.
no, it is interacting.
Yeah.
Oh, you
It's
mean
a
the
self-
zero range interacting version? I see.
Exactly, zero range. That's right.
How many terms do you take in the separable potential?
How many terms? What do you mean?
Just one term separable.
It's a single term.
It's a single. Just.
So how can you reproduce the scattering length and the effective range with just so there's some range in the potential, and
Yes.
it seems to me if you have a single term, you just have two parameters, right?
The chi is a function.
Chi is a function.
It's a
So you have infinitely many parameters in a sense. It depends on this continuous variable Q.
Oh. Okay. All right.
Yes.
But actually,
So then you have infinitely many. Well.
Yes, you have infinitely
reproducing
many.
many terms.
That's right.
reducing
That's
the
right.
effective range to that relation you showed before. Right?
Absolutely.
The effective range is related to the integral over what a nuclear physicist would call the wound integral, right?
The what?
The wound integral.
Wound integral. Okay.
This difference you showed.
Yes,
We call that the wound integral.
Let me show it again.
It's fun to say.
Oh, that's too far away. Sorry. I should have. Yes, this exactly this expression.
Yeah, so that's right. So
Yeah.
So because you have that relation and you have the size 0 bar, you
Ab-
have the effective range too.
Absolutely. Yes. All right. So let's. Oops. Sorry. All right. Yeah, so let me show you an example. So that's for a van der Waals interaction. I guess it's a Lennard-Jones potential again. So this is the two-body energy as a function of the inverse scattering length. This is what you would get for an exact calculation of this van der Waals interaction. Here, this is the universal dimer energy, which scales like 1 over the scattering length. So you see it's good only for very at very low energy. And this is the result we get from this separable potential. So, so here you can see where it works and where it doesn't work. So in this region, it works pretty well, and it works much better than this universal law. But what you see that when the energy is exceeds the van der Waals energy, then it deviates significantly and becomes completely wrong. So it's not as powerful as say the quantum defect theory that Paul showed yesterday, But it's reasonably powerful for this kind of approximation. So at least in this low energy region, it works quite well.
Pascal, it looks
Yes.
like it might fit about as well as the Vogel-van der Waals formula. I'd be interested to compare it against that.
Yes,
or
we can
binding
compare.
energy versus
You mean the
standard
expansion yes,
Yeah.
but that's just an arbitrary truncation in this calculation, so it can be, I mean, depending on which order you stop, then you can get better or worse than that. So.
What is the vertical axis? I can't read that.
Sorry, the vertical axis is the energy. So this is the energy of the last bound state.
Energy, the last two-body bound.
Two-body bound state. Yes, sorry, two-body bound state. Does it make sense? Or?
Okay.
So in the universal theory, the two-body bound state would just be, just get 1 over a squared, right? And
should go a little further with a separable potential.
yes, yes, and a separable potential which is adjusted to reproduce this the bound state of this potential. Yes.
Okay.
If you add more terms, can you reproduce it further in energy and?
You mean more terms? You mean here?
Yeah.
Yes.
Like more? Yeah, presumably yes.
This is
That's
actually, I mean, obviously I haven't done this calculation, but the technology to do that is actually well known, right? Because you can force the separable to reproduce the underlying T matrix at some set of energies, right? And so you could pick a set of points where it looks exactly like the van der Waals wave function, and
right.
after that it essentially becomes an interpolant, right?
Yes, I believe so. Yes.
So what it looks like, you're simulating the variation of the energy scale that is set by the van der Waals potential by reproducing the nodal pattern of the two-body wave.
Yes, that's right.
Okay.
Any other question? No. So then once we have this simple model, then we can do a three-body calculation, and it's very easy. I mean, the kind of equation you get for this potential is a single one-dimensional integral equation that can be solved in just a few seconds. And then you get this kind of curve for the ground state three-body energy. And so this is just a zoom on in this region here. So here in this region, the agreement for the two-body bound state is excellent. And here I do the three-body calculation. And of course, I can extract this binding wave number and this dissociation scattering length as measures of this three-body parameter. So then let's look at the results. So for example, if I take this, this is the zero energy two-body wave function for Lennard-Jones potential with 5 S-wave bound states. And I use this as an input in this separable potential. And then I do the three-body calculation, and I get A minus, which is minus 10.9 times the van der Waals length. So that compares reasonably well with the exact calculation I showed before, and well, also the experiments. Now, you might think, actually, when I got this result, I thought, well, okay, it's nice, but is it really a good result, or is it just a coincidence? Because this separable potential is a bit funny. It's a non-local potential, so it may be that the short-range physics is completely different, but then by some accident I get some value which is nice. So to check this, I plotted the probability density as a function of the hyperradius, integrating over all the other variables, and I get this. So this is a three-body bound state, so it decays exponentially like this. And then at short distance, you can see that there's a very nice and simple behavior. The probability is gradually suppressed at around twice the. So this is in unit of van der Waals length. Sorry. So around twice the van der Waals length, as we expect. So it's very consistent with the picture I showed before. So so it seems to capture the physics quite right.
If you change the number of bound states to be 3 or 10?
Yes.
Does this?
Yeah, it's very stable actually, because the thing is that most of so this value depends essentially on this part of the two-body correlation. If you change the number of bound states, you will change here the number of oscillations, but it's a very small difference. It doesn't make much difference actually.
So what digit changes in that 10.86?
So initially, it's I can look up the numbers, but for just one bound state is a little bit different. It's a bit less than 10, I think, and then it converges quite. I can check the numbers. I can tell you.
Did you try to convert density into an effective potential, just to see quantitatively what?
No, that's a good idea. I haven't done that. Yes, that's a good idea. Yeah. Okay, and then what about other potentials? So there's actually a very nice paper from year 2000 from these authors where they essentially, they didn't phrase it in terms of ephemeral physics, but essentially what they calculated is this parameters for many different kinds of potentials. So here I just showed a few: the Yukawa potential, exponentially decaying potential, Gaussian, Morse, Purcell-Taylor, and many others. And these are the results that they found. And so, so now with this method, we can try to reproduce this result by just calculating the two-body wave function for this potential. That's very trivial thing to do. And then put it as an input in this potential, and then do the three-body calculation. And we got these results. So it's not perfect agreement, but it's quite close. In a more graphical way, so here this is the binding wave number, the exact value versus the one we get in the separable model. And oh, this, well, there's supposed to be some gray area here, but we don't see it anyway. So anyway, I just wanted to show that it deviates by less than 10% from the exact result for all these potentials.
So is it over-interpreting to think that the deviation grows with kappa?
I'm sorry?
Is it over-interpretation to say that the deviation grows with kappa?
The deviation grows with kappa. Yes, that could be. That I don't know.
Is it really deeply down?
Yes, that would make sense indeed. Yes.
Is there any simple explanation as to why it tends to be mostly systematically below the line there?
That I don't know. That I don't know. I mean, I was wondering also.
What determines the line?
Oh, this line here, this is just the identity line, just to show. I mean, if there were perfect agreement, then they will all be on this line.
All be on a line, but what is that specific line? Isn't that a specific slope?
Yeah, it's slope 1.
Just slope 1.
Oh wait, it's kappa? It's kappa.
So this is kappa versus
Oh,
kappa.
yeah.
Yes. Sorry. Yes.
I see.
So this is just for the purpose of comparing, you know, the exact. I mean the value we get with the exact value, and you know it's pretty close to this line. It's not perfect, but it's. Yes, so that convinced us that indeed this zero energy correlation captures a lot of this three-body parameter physics.
What is this single point that sticks out?
This one?
Which potential is that?
So this one, that's a Purcell-Taylor potential for parameter alpha equals 9.
And what is this?
So
Number of bound states?
no. It's
What is
I don't remember the formula by hand. It's
Hyperbolic sequence.
yeah, that's right. That's a combination of hyperbolic second and some other hyperbolic function, and there's a alpha parameter. I can show you, but I don't remember the formula now. Yeah, I don't know why actually. Only for this value, it's above the line. For all these other values, it's actually below. So I don't understand how these deviations work. But
for these potentials are they deep in the sense that, for example,
No.
they contain P wave, D wave, higher order?
all these potentials are fairly shallow, so they only have one S wave bound state. Okay, so now just intermediate summary. So we start from the two-body correlation, which again is the zero energy wave, two-body wave function, and the typical length scale associated to this is the effective range. This creates a three-body deformation, which causes a three-body repulsion, and in the end sets the three-body parameter to something which is on the order of the effective range. So just a little note here. You might think that this actually very natural, that maybe you might think that, well, actually, if we do a low energy expansion of, say, the scattering phase shift, first we get the scattering length as the first order, and then we get the effective range as the second order. So it sounds very natural that this is what we get here. But this is not what I'm presenting here. Really, in order to get this result, we had to use the two-body correlation, and that means, as we mentioned before, the off-shell of the energy shell elements of the T matrix. The Born expansion of the scattering phase shift concerns the on the energy shell elements. So it's not the same thing here. So just to make this point. All right, and now once we understand this, we also understand that if this two-body correlation has a universal form, as it happens, and Paul showed yesterday that it is indeed universal for van der Waals interaction, then we naturally expect that the value of the three-body parameter is also universal. So, and that's the case in general for not only van der Waals, but interactions decaying as power law, 1 over r to the n. So here I represent, so here this is for the case n equals 6, so van der Waals. This is kind of Lennard-Jones potential with only one S-wave bound state. But this is very similar to, say, the interaction between helium atoms. And so what you can see here is that, okay, this is the two-body probability as a function of the interparticle distance. And of course, here it's suppressed because you have this hard core, so that seems very natural. And you might think that the form of this wave function here is due to this hard core repulsion. But actually, if we make the potential deeper, like this, then this is the corresponding two-body wave function, and we can make deeper and deeper. And what you can see is that what it creates here is these fast oscillations, which are due to the acceleration in this deep potential. But in all cases, the two-body wave function looks very similar, because so in the first case, it's suppressed by this hard core. In the other cases, it's suppressed by the strong acceleration in this potential. But the end result is more or less the same. You have very small probability here, and then in this region above 1 unit of van der Waals length, you have a two-body wave function which is very similar and actually is known analytically. It can be expressed in terms of this Bessel function. So in this sense, there is a universality of the two-body correlation, and as a result, we obtain this universality of the three-body parameter.
Pascal, that's an infinite scattering?
Oh, I'm sorry. This is for infinite scattering lengths. That's right. That's right. Yes.
Well, what's R sub n?
What's R? Yes. So, oh, sorry. I didn't put the formula. So R sub n is the length scale associated to the tail of this 1 over Rn potential.
The analog of what you wrote there, but for
exactly. Yes. That's right. So you can generalize this formula. And I can give you I don't remember by heart, but yes. Yeah. And for n equals 6, it reduces to this one.
At the top, do you have the restriction n greater than 3? So is n
right.
3 a problem?
Well, it's just that I restrict myself to so-called short-range interactions, which is the original setting for the Efimov effect. And in order to have, I mean, in scattering theory, an interaction is short range if it's decaying faster than 1 over r to the 1 over r cube.
I thought r cube was just enough to treat it as short range.
For r cube, I think you cannot define the. So if you have an isotropic r cube interaction, 1 over r cube interaction, you don't have the same concept of scattering lengths. You have to define it slightly differently, as far as I remember.
If it's attractive, you can't define the scattering lengths in that case. If it's repulsive, you can still define it.
Okay, yeah. So that's why I restricted myself to this.
So how is Rn related to the van der Waals length?
So Rn is the van der Waals length for n equals 6, and for other n, then it's just a.
Is it somehow related to the turning points of the potential, or?
No, it's related to the
it's
to the tail of the potential. So that's
C sub n to the appropriate power.
Yeah.
This is C6.
So the way you get it is, okay, you have this energy scale, which is you have some kind of Cn over Rn, and that's the energy in the tail of the potential, and you compare that with the kinetic energy, and by doing that, it gives you a length scale, and that's this Rn.
So when you vary the depth of this potential, right?
Yes.
But each time is set at the resonance.
That's right. That's right.
Fix,
that's right.
At the resonance.
Yes.
So I would imagine for different depth of the potential, the effector range, or just if we do the expansion for the phase shift, right? So then the effector range or some other just higher terms, those parameters can be a little bit different, though they may be of the same order.
Yeah, so that's the point. So for this kind of interaction, the effective range actually has always the same value at unitarity. So you can make
the same value.
the same value. That's right. And you can actually So the effective range has a very well defined value in terms of this Rn.
Yeah. Then if I expand the phase shift to higher orders, say the next one.
Oh yes.
I can imagine it can be different, right? If it's different, then would I expect the difference between these wave functions is of the order, say, the energy times the difference of these parameters?
Yes, I believe that these higher orders will correspond to the fact that you don't have the same number of oscillations, for example, at short range, yes. But this makes only minor differences, yes. Okay, but then we have other potentials, those decaying faster than power lattice, like this Gaussian or Yukawa or Purcell-Teller, etc. And they seem to have quite different behavior. So here I just represented again the zero energy two-body wave function at unitarity for various depths. So I just multiply this potential by some constant, by some factor to make them deeper and reach unitarity. This is for one single S-wave bound state, two bound state, 10 and 100. And well, first thing you see that the correlation shifts like this, which means that the effective range is increasing. So it's not the best representation, which it's more natural to scale this wave function in units of effective range, which is what is represented in the main graph. But still, if you do that, you see that they don't superimpose nicely as they did before for the power law potential. So it seems that there's no particular universality emerging from the two-body for these potentials. However, one thing that you can say is that if you consider extremely deep potentials, then eventually you can show that these two-body wave function converge to some kind of step function like this. However, you have to really have very deep potentials, and that's very, very dissimilar to the situation where even for the very shallow potential, it's almost universal already.
Well, yeah, but here the potential you show us, compared to the one on the left, right?
Yes.
The one on the left, you have a rather just a hard core, repulsive hard core.
Yes.
Plus this tail, attractive tail.
Yeah, but the hard core is not essential, actually. It's
okay. So if you do the calculation for the right side, you can also show that if I add a hard core.
That's right. Yeah, I also did calculate. I didn't show there's also the most potential, for example, which also has a core. Well, it's not as hard maybe, but still there's a core, and you get the same.
But what is when you add a hard core to these potentials? I think that was the question.
So when you add a hard core, I think it suppresses the probability at short distance a bit. So for example, for this state here, you will get, instead of something like this, you will get something more pronounced. But still, it will not converge. It will maybe help a bit, but it doesn't change much. Yes.
On the left, on the left side.
Yes.
That's the plot for n equals 6.
That's right.
And if you plot it for n equal 4 compared to n equal 4 and 6,
yes.
Are they a little bit different?
It looks similar. It's a bit stretched, but I can show you actually. I don't know if maybe I can show later.
But the big difference between the power law and these other potentials is that the power law has a single length scale.
Right. Right.
These all have at least 2, possibly more length scales. So you're not really going to see that same sort of scaling behavior where you're changing one length scale but leaving the others fixed.
Right. Right.
Might does the Gaussian potential have more than one length scale?
Well, you have
the strength, the length scale and the strength and the length scale
yes.
the size of the Gaussian.
Right.
But Leonard-Jones has also.
Well, Leonard-Jones also has two length scale, but
one of them is just the short range stuff.
Yeah.
Which
well, let's say that for the power law, the only one length scale among the two is playing an important role. Where in this case, the two length scale just yes.
Long range length scale.
Right, it's a long range.
You have more than one long range length scale.
Yes.
In Gaussian, you have only one, because if you tune it to the unitary point, you have to use your.
Yeah, but you have several choices of depths for different number of bound states. So in that sense, you still have some. Yes.
But if you want to stay within that state.
Right. No, but I think that the point is correct, that the two length scale here are both short range, and therefore there's no universality appearing.
I don't know if there'd be any way of trying to scale them together to.
Yeah, I thought about it, but I couldn't find any. I mean, they look more or less the same because, I mean, it has to look more or less the same. I mean, it's just a decaying potential, but there's no, at least, obvious mapping. Okay, so then this is the final plot. So here I represented, so for all these various interactions, so power law interaction and decaying faster than power law interactions, the value of the binding wave number as a function of the number of bound states. So each point is at unitarity for a different number of S-ways bound states. So again, for the power law potential, like 1 over r to the 4, 1 over r to the 6, you get something which is fairly constant because of this two-body universality. However, for these other potentials, so at first you get different values, but eventually it converges to this kind of step function correlation, which you can calculate actually numerically, and you get this number. And you see that it converges very slowly, but it converges to this number. So right, so then this is the why we say that there are different classes of universality of this three-body parameter. And so, by the way, this region here corresponds to typical situation in atomic physics. This region here corresponds to the typical situation in nuclear physics, where you have very short-range potentials with a few bound states. And this, I don't know actually, if any of you have some idea of what physical system it could correspond to, then it would be very nice if this could be seen experimentally. Okay, so then I reach again my conclusion, so the same as before. So it seems that the three-body parameter is essentially determined by the two-body correlation, and again by that I mean the zero-energy two-body wave function. The reason is that the two-body correlation was essentially when it creates a suppression of probability, induces a deformation of the three-body system, and the consequences is the three-body parameters is typically given by the two-body effective range, and there are distinct classes of interaction for which the three-body parameter has a universal value. All right, so thank you for your attention.